Welcome. This is lecture 37. So in this we continue our discussion about Artinian rings. Okay. And then we would like to discuss about graded modules over Artinian local rings. Okay. This is graded modules over polynomial rings over Artinian local rings. Okay. So this is the plan for this lecture, and so Artinian rings, we are just continuing our discussion from the previous, just to give a specific example or one place where it shows up. So proposition, let K be an algebraically closed field. So this assumption is only to say we can visualize the solution set, field. Okay. R polynomial ring in K in n variables. I an ideal of R, okay. Then R mod I is Artinian if and only if Z of I, the solution set of I, is finite. Okay. So we can remove this this hypothesis that K is algebraically closed. Again, that is used only to say that if Z of I is finite, then there are only finitely many maximal ideals, okay, in that ring. It may not be true if K is not algebraically closed. It is possible that Z of I is infinite, but Z of I is empty, but the ring is not non-trivial. Okay. So it is to avoid those situations that we are assuming K is algebraically closed. Okay. So let's so just a remark before we prove. We already know this. We have already seen an equivalence of this condition. Recall that Z of I is finite, okay, if and only if, okay, this we proved a little while ago, that rank of R mod I as a K vector space, this is as K vector space. So as I mentioned in an earlier lecture, we have to use dimension in two different ways. One is a vector space dimension and the other one is Krull dimension. So we will try to use the word rank whenever we talk about vector spaces. Okay. So this is finite, and then we also saw that this is equivalent to the condition that Grosvenor base, every Grosvenor basis, meaning that is for every monomial order contains a term with xi to the ai for all I. It contains an element with this as the leading term. Okay, so sorry, every Grosvenor basis in any monomial order contains an element with the leading term xi to the ai. For every I, this is true. Okay, so for all I and for all Grosvenor bases, there is a term with this leading. Okay, and this was the equivalence of all this we had proved earlier. Okay. So again, it doesn't one does not need Zi to be fine. case need to be algebraically closed. One can reformulate it in terms of spec of R mod I, but for us to visualize it, it's better to state it in this geometric fashion. Okay, so let's prove the proposition. Okay. If Zi is finite. Okay. So notice that R is Noetherian. Okay. So therefore, the set of minimal primes of R mod I, which is a subset of the associated primes of R mod I, is finite. Till now, we had not seen a proof, or we did not know that minimal primes over an ideal in a Noetherian ring is finite. So this is a proof that we know that associated primes are finite because associated primes are precisely the primes that appear in an irreducible decomposition. Starting with an irreducible decomposition, we can make it irredundant primary decomposition, and associated primes appear as associated to one of those things, and therefore this list is finite, and hence this is finite. Okay. So this is so minimal primes are finite. Okay. So let P be a minimal prime over I. Okay. Then Zp is a subset of Z of I. So this is also finite. Okay. So we want to show that if Zp is finite for some prime ideal P, then P is maximal. Okay. So write Zp as Zm1 union Zmr. So Zr, where M1 through Mr are maximal ideals. And Z1 is the point corresponding to that maximal ideal. Okay. So we can write it like this, but this is, remember that this is equal to, also equal to Z of M1 through Mr, the product or the intersection, whichever one. Okay. In other words, these two ideals have the same radical, or since P is prime, this is a radical ideal. So now this implies that Z M1 Mr is inside, I mean it says that these two have the same radical, but since P is prime, it is its own radical, so this is inside P. Which now implies that Mi is inside P for some I, okay, but this is maximal, so P equals Mi. Okay. So prime ideals in which if P is a prime ideal such that Zp is finite, then P is maximal. Okay. So it is in this thing that we use that K is algebraically closed. Okay. I mean, it is possible that P is a non-maximal over a non-algebraically closed field. It's possible that P is a non-maximal ideal, but it has no solutions in that over that field. Okay. Okay. So conversely, this is the only if. Yeah. So this proves that P is maximal, but then remember where we chose P from. P was from minimal primes, so every minimal prime is a maximal ideal. Maybe let's just write that and conclude. This now implies that minimal primes over R mod I is inside max spec of R, which is what we wanted to prove. Okay. Yeah. So then, I mean, this one would imply that some power of the let's let's add the details. Okay. So but this is finite. So then this implies that min over R mod I is some sets, let's say M1 through MS, not necessarily the ones that we saw, some other M1 through MS, maybe just to be safe, let's call it N1 through NS, maximal ideals. Okay. So now this implies that radical of I is the intersection of these maximal ideals. Okay. But from which we can conclude that R mod I is finite length, because some power of this will be inside I and these all have finite length. So R mod I has finite length. In other words, it's Artinian. Okay. So this is the direction of if, and for only if. Okay. Now it is Artinian. So Artinian means that R mod I Artinian, which now implies that the every prime ideal in R mod I is a maximal ideal. Okay. This now implies that V of I, which is all the primes containing I, is inside the max spec of R. Okay. This is primes containing I and maximal ideal of R mod I. So they pull back to maximal ideals in R. So we get this condition. Okay. But we need to show that it is actually finitely many points, since R is Noetherian. Okay. Min I is finite. Okay. But what is in V of I? V of I is prime which contains some prime in min I, but then they are all maximal, which now says that I, the minimal primes of I, minimal primes of R mod I, is a finite subset of max spec R. Okay. Remember, minimal primes are the minimal elements in V of I, but they are all inside here. Okay. And among them there is no comparison, so they are all pairwise incomparable. So this is inside here, and so therefore Z of I is Z of M1, Z of some Mn for some maximal ideals M1 through Mn. Okay. So this is not the variable n, but some other p, let's say. N was the number of variables. This list has one collection cardinal. This could be more, or has no relation to the number of variables. Okay. So this is okay. So this is the proof of this. Okay. So now let's try to take a look at Macaulay, an example. So I will also try to. So it's a relatively simple example, but we will try to sort of use things that we have learned so far to understand that ideal. Various things that we have learned so far, we will try to use on that ideal. Okay. So here is an example. So we take a polynomial. So again, just let me just remind you, this is the first line. Ignore the first line, that's not part of the code. Just these 3 lines that are offset. Z just ignore that line. Okay. So polynomial ring in 3 variables, and I is an ideal generated by three things. So let's just quickly look at what it is in the if we were looking at in R3. So this is a cone, at least in the positive part. Okay. When Z is positive, this is a cone. This is a plane which will intersect the cone, because well, 1 1 1 is a solution, and so is for this one. Okay. So just by looking at itself, we know one point in the intersection. So and since these coefficients here are substantially less than 101, whatever calculation that happened in R will also happen identically in this field. So 111 is going to be a solution. Okay. Because the coefficients are integer. So in principle, one can ask those relations over any field, not necessarily over R or over the field that is defined. Okay, so here we ask for a generators of its Grobner basis, and it produces something. And so if you look, there is a term here with x, there's a term here with y squared, and then there is a polynomial here with leading term z cube. So from the test that we have learned earlier, this will have finitely many solutions even over the algebraic closure. Okay. This is of course a finite field, so it will have only finitely many solutions. But even over its algebraic closure, it will only have finitely many solutions. Okay. So now let's let's look at the minimal primes. So if you ask for the minimal primes, what will happen is it will produce some long list which will be unwrapped, unwrapped line going out of this page. So I just try to print them one by one. Okay. So I ask Macaulay for minimal. There's a command called minimal primes. Okay. So take a look at its help. Take a look at its methods. So if you ask methods minimal primes, it will tell you the ways in which methods minimal primes can be used, the types of the arguments. So call it min I. Then I ask, so we have seen this. This is an abbreviation for the apply function. So this is the same thing as apply to min I this function. P maps to print P. Okay, so it just prints and does nothing else. Okay, so these are the things. And as I mentioned earlier, we know that 111 is a solution to this. I mean, okay, so it has some solution even over any field. Okay, so we ask, yeah, y minus 1, x minus 1, z minus 1 is an ideal which contains this, and then it produces something. And of course, depending on what field you put, these coefficients might be different. So if you put, instead of 101, you put some other larger field, these numbers might be different. Okay. That of course depends on these numbers will depend on what field we are working over. It may not actually have any solution over R. I didn't check, but it may not have a solution over R. Okay, over R, maybe one would just see this and some other. Okay, so even if the equations involve only integers, what the primary decomposition will look like will depend on the field. Okay, so please keep that in mind. So as I said, we could have guessed the first one by looking at the generators of I. These three other minimal primes. Label the above minimal primes P1, P2, P3 in that order. P1 is that one, P2 is the one with this, and P3 in this order. So we ask, okay, we would like to understand what is the primary decomposition of I, meaning I equals some J1 intersect J2 intersect J3, J1 associated to P1, J2 associated to P2, J3 associated to P3. We would like to understand this, but so we'll see if we are lucky enough, and we ask, just intersect these three prime ideals and check, is it equal to I? So then it says no. Okay, so that's too bad. And then let's look at the next. So we saturate. So now we try what we know. If you want to find associated or primary components that are that don't contain a specific element, saturate with respect to that element, and then try to find a primary decomposition. So let's saturate I by x minus 1. So it's going. It will try to find components corresponding to these two primes. Okay. So first I saturate that, and the second time I saturate with respect to x plus 32y minus 9. Yeah, x plus 32y minus 9. Okay. So we are looking for this prime component corresponding to this prime. Okay. So then it produces some ideal. Okay. So now this would be this ideal will be primary to P3. Okay. So this will get rid of P1, this will get rid of P2, and so what is left over will be primary to P3, since that's the only other prime ideal. And if we look at it, this looks very prime-like, because there is some linear thing here, there is some linear thing here, and then some z square. So this might be prime. I mean, by looking at it, we just feel, okay, this might be prime. Okay. So then we ask, is this prime? Is this ideal that we got, which I called I12, is that equal to the last one in that list, min I? Okay. So what was min I? Min I was these three. Min I was these three. P1, P2, P3. So we remove P1, we remove P2, and we got some ideal. And since that thing looks very prime-like, we see if we get lucky and ask, is it equal to, is I12 equal to last min I? And it says it's true. So I12 is P3, and it is the component corresponding to P3. Okay. So now we will remove P. We have already removed P1. We will remove P2. We will now remove P3. So this is the this is what we did. Okay. So remember, P3 is P3 has this x minus 41y minus 35. So we remove that now. Okay. So we remove that now here. Okay. And then we get. Okay. So then we ask, is this the middle one? Middle one is P2. So remember, list is numbered from 0 to length minus 1. Okay. So 1 means the second one in the list. And so we ask, is this saturation? So we get some ideal here. Then we ask, is it equal to min I? And it says true. So therefore P2 is also a component. Okay. So then we become sort of hopeful, and then we ask, okay, let us now saturate. Okay, so I just put this in one line. First, we saturate that linear form in P2. Of that thing, we saturate the linear form in P3. Okay, and then we ask, we get some ideal. Then we ask, is this equal to? So this is the component for P1. Okay, so z minus 1, x plus y minus 2, and y square minus 2y minus 1. If you notice, this itself is not over that field. This itself is not a prime ideal. This is not same thing as P1. But if you notice, if you go to its algebraic closure, it has only one. I mean, z of this ideal is just 1 point. Okay, the zero set of this ideal is just 1 point. Z coordinate is 1, and if we solve this, this one says y coordinate is 1, but with multiplicity 2, and that will solve x coordinate also to be 1. So this is, I mean, the component of P1 corresponds to the maximal ideal at 1, 1, 1. The component is an ideal which is not exactly P1, but something which is just only primary to it. Okay, so this is not the same as P1. Okay. And then we just check that we got the correct answer. We intersect the last one that just got output and then min 1, and we already concluded that min I1 and min I2 are already the associated components corresponding to the P2 and P3. So we just intersect. So of course we'll get some, because intersection, remember, involves extending to some bigger ring, so t times I plus 1 minus t times j, and then contracting it back to R. So we get some really long list of generators, and then we just ask, is this same as I? And the answer is yes. Okay. So this is an example where we work through an Artinian ring using various techniques that we have learned so far about saturation, finding minimal components, and so on. So the only thing that we actually, in this example, only thing whose algorithm that we have not studied is this minimal primes. So that one has to, I use that to get this list and then proceed from there. Okay. Okay. So now we want to discuss a new topic called graded modules. We will not discuss them in more generality than what we need for the present, which is the following. So R is an Artinian local ring. S is a polynomial ring over R in some variables x1 through xn. But not just, we put an extra structure which is natural to this one, which is the degree. We say degree of xi is 1, okay, for all I. Okay. Okay. So this gives a decomposition of S as direct sum of Si, I non-negative integer, where by Si we mean this is as R modules, okay, not as a ring but as R modules. By Si we mean the R module, actually free, generated by monomials of total degree I, that is x1 to the a1, xn to the an, such that this set such that ai is non-negative for all aj is non-negative for all j, and sum of ai equals 1 is I, sum of aj equals I. Okay. So this is a free module. This is just a basis. So it is exactly like a polynomial ring over a field, except that the coefficients we now allow for Artinian rings, and polynomial ring always has a, depending on what degree one wants to give to these variables, and for our, I think all that we need is this, so we'll just stick with that thing. So, okay, only point that we allow for some freedom for here to be Artinian local rings. Okay, so this is the, this is called a graded ring. So in this particular case, it is graded by Z, although it lives only in the non-negative degrees. Okay. So S is a graded ring. Okay. We'll come back to graded rings later after we prove these somewhat technical things and use them extensively with Macaulay too. But right now we just develop enough for us to go through this. Just enough to understand how to discuss dimension of Noetherian rings. Okay, so this is a graded ring. And what is the other property? If we take polynomials, elements of Si, and multiply them with elements of Sj, this is inside Si plus j for all I, j. Okay, and we will say that this is Z graded, or we'll just say non-negatively graded, because in this case this is so first Z graded means that the grading is controlled by integers like this. N graded in particular says that it is 0, the graded parts are 0 in the negative degrees. Okay, so that's all. Okay. Now, an S module M is said to be a graded S module if M has a decomposition, M has a decomposition, M equals direct sum of Mi, and here we would allow for all elements in Z, all indexed by integers, okay, as, so remember any S module is also an R module, so as R modules, okay, such that Si times Mj is inside Mi plus j for all I and j. Okay. So elements of degree I will multiply elements of degree j to elements of degree, and the result will be elements of degree I plus j. Okay. So this is what we mean, and for any I, for all, so just one piece of notation, for all I, elements of Si or Mi are called homogeneous of degree I. Okay. I mean technically the union of Si, not the direct sum, the union of Si element are called the homogeneous elements, and if I belongs to S, if F belongs to Si, we say its degree is high. Okay, but I hope this is clear. Homogeneous means it belongs to one degree piece, not a sum of two things from two different degree pieces. Okay. So one observation that we want, note that S is Noetherian. Okay. Now we would like to understand what M. Okay. So M, a graded module M, let M be a finitely generated graded module. Okay. Then, if we take, first of all, it is finitely generated. Okay. So then, note, or maybe exercise. So just by saying that, it is not asserted that it has a generating set of homogeneous elements, but the exercise is to show that M has a generating set of homogeneous elements. Okay. Sorry, that does not need a finitely generated. You can just, you don't need this. Just graded module means it has a generating set of homogeneous elements. Now assume that M is finitely generated. Okay. Then there is a least degree of a generating set. So let G inside M be a set of homogeneous generators. Okay. So this is finite. So let D be min degree of G where G is in G. Okay. So among the generators, take the least, among the degrees of the generators, take the least number. Okay. So now this implies that Mi must be 0 for all I less than D. Okay. So that's the first observation. If you have a finitely generated module, then in sufficiently negative degrees the modulo 0. Okay, so that's one observation. The next observation that we would like to make is so now by induction, so let's say that, so let's take such a D. Okay, then for all I greater than D, okay, if we look at the module greater than or equal to D, okay, if you look at J direct sum J greater than or equal to I, okay, so maybe I'll just draw a sketch of what, so there is, so let's say this is negative degrees, this is positive degrees. Okay, at some sufficiently negative degree we have zeros. Okay, then something happens, then here is MD. It does not say D is positive or negative, there is some D. Okay, so here there is stuff. Okay, so now take some I bigger than or equal to D. So take this module, okay, take the direct sum of all J greater than or equal to I. Okay, so this one. So this is an S submodule. Okay, so this is an S submodule of M, graded submodule of M. Okay, therefore it is finitely generated. Because S is Noetherian, this is module is finite, M is finitely generated. So which now implies that if you take this sum for J greater than or equal to I modulo J strictly greater than I is finitely generated. S module, of course, because it's quotient of an S module, but it is finitely generated as an R module. Okay, so the observation that we want to make is, if you take S and go modulo the ideal generated by the X's, which is the entire positive part of S, this is isomorphic to R. So if you use that thing, we conclude that, okay, so but what is this? This is just, as an R module, this is same as Mj. Okay, so if M is finitely generated, then in sufficiently negative degrees it is 0. And moreover, every homogeneous part is a finitely generated R module. Okay, so this is an observation that we would need to use. Okay, so we will continue discussing graded modules in the next lecture, and we'll prove a theorem about their lengths.